Swayam Prabha. Digital India. Educated India.
You can see here in the diagram which or the circuit which is mentioned here, and in the Cockcroft Walton accelerator you can see that a rectifier or a multiplier produces a high voltage applied to the accelerating column, and that accelerated column is used for accelerating the particles. Now, what is this Cockcroft-Walton type accelerator? In a simple voltage, it's a simple voltage multiplier, where a AC voltage charges the capacitors. Now, you have seen that when we discussed about the two plates, there we were applying a battery or a voltage source which were DC. Now, here that DC voltage is replaced by a AC voltage source, and that will be responsible for going to much higher voltage, because once you are using a DC voltage, the capacitor can be charged only to that voltage. While in this case, they use the AC source, AC voltage, and then by using several units, the much higher voltages could be used. So these they charge the capacitors, and these two people, Cockcroft and Walton, they basically built a multiplier, voltage multiplier, and that was connected to column section, and that is accelerating tube, and the many experiments were done. In fact, these two scientists, they performed the first artificial splitting of nucleus atom in 1932, and for this what they did was that they accelerated proton beam to about 600 to 700 keV, and they bombarded lithium-7, and they found that it gets converted into two helium nuclei. So you can say this was the first experiment of splitting the nucleus using accelerated beam. As I mentioned earlier, that before that all the experiments were done using alpha particles from the radioactive ion sources. So this was the first experiment done using artificially accelerated beams, and where the nucleus was split. In this case, for example, lithium-7 is split with the bombardment of proton, and two helium nuclei were produced. In fact, at that moment it was such an exciting experiment that they got Nobel Prize in physics in 1951 for this splitting of atoms nucleus. So you can see here, just to give you the configuration, that there is a transformer here where AC voltage is applied, and across this you get a voltage which is V is equal to V naught sine omega t. So this has a AC voltage has a frequency of omega, and it's a sinusoidal wave. So this is the one, and in subsequent lecture, subsequent transparency, you say that how the system works. So basically it is a network of capacitors and diodes. And diodes are used, see, when you were using a DC voltage source, you could use the resistance. But here, because the voltage is also going to negative, and therefore you cannot use resistance for charging the capacitor, because otherwise the current will flow in the reverse direction. If AC voltage is used, then in one cycle half cycle it will flow, it will charge, and in the other half cycle it will discharge. So you will not get any voltage. That is why in this case you have to use diodes, and I have already talked about the characteristics of the diode, because it functions in forward bias and the reverse bias. So these are two circuits. For example, in the first one is a single stage. Here you can see here this is a source which is a AC voltage, AC source, and if A, for example, is positive, in this case positive, then this diode which is D1 will be forward bias, and there will be current flowing in this circuit, and as a consequence of that, this or condenser will be charged to a maximum voltage of V naught. While when it becomes negative, then you see when this is negative, then this will be reverse bias, so this will not conduct. Then this circuit will be active, because this is negative and this is positive, and then this will be charged, and that will be, it will be charged to 2V naught, because this is V naught plus the voltage here. So you can see that this is a circuit which can also be shown here in the negative. For example, this will not be charged, because this will not be active, so it will be charged, this will be charged through this circuit, because this is now forward diode, this is reverse and this is forward. So this circuit which will be using here for charging is here, and this C2 will be charged to 2V naught. V naught is the maximum or the peak voltage of this AC signal which you are giving here. So the same thing is explained here, that during the positive half cycle, that is this, the point age is positive, and the first diode D1 is conducting, that is forward diode, and C1 will be charged through diode D1 to V naught. In the second case, when the voltage is negative, then D1 is reverse bias, but D2 is forward bias. So then circuit follows is here. So you will get same thing is explained here, and I have already told you that in the case when this is not DC voltage, then you cannot use the resistance, because in the case of resistance there is nothing like forward or reverse bias, and therefore if in the positive polarity, when this is positive, let's say this is charged or it is raised to the voltage, when the polarity changes, then this will be discharged, and there will not be any voltage across this. This is also shown here, the same thing which I have all. So this basically was so what Cockcroft Walton did was that instead of having just one unit, which is shown here, this is one unit of multiplier, and one unit or one stage is having two capacitors and two diodes. While if you want to go to higher voltages, then you can keep adding these stages, and of course you can't go infinitely, because then there will be other problems. So this is how the Cockcroft Walton works, and you can see here that this is basically a 3 stage. So one stage, 1, 2, 3. So like this it will be 3 times voltage, and each capacitor is 2 V naught, so it will be 6 times of that V naught. So this is how it works. Now in this case you can see that there is a capacitor of capacitance value C, and the capacitance value, calculation of capacitance value is very important, and for two parallel plates it is given as epsilon 0 A upon D. A is the area of the plates and D is the distance between them, and epsilon naught is the permittivity of air. So this is the relation of capacitance for two plates where the medium is air. While if you are using some other medium, then it is gets multiplied by epsilon r, where epsilon r is a relative permittivity of the medium. And that you can see that it by putting, for example, in the case of we have done it, suppose you put enclose this system into SF6, which has higher dielectric constant, you can go to higher voltages. So this is how the DC Cockcroft Walton type DC accelerator works, and I will further explain because you have to understand it, that how the charging and discharging takes place. So these are some of the things you can see, that is a set of capacitors and the diodes. So you take that first one. If suppose the AC voltage is applied, which is V naught sine omega t. So first one is positive. Let's say this is A and this is B, which is shown here. Now if A is negative, this point is negative with respect to this ground. So this ground, then this diode will be forward biased, and for charging the current will flow through the path which is shown here in red. So in the first positive half of the cycle, this will be active and this capacitor will be charged. In the next half cycle, this see earlier this was negative, now it becomes positive. So when it is positive, then this will not conduct, and so this will take, this becomes positive and this becomes negative, and therefore in the second half, which is negative cycle, then this current will flow through this cycle. So this condenser will be charged, this capacitor will be charged to V, twice of V naught, and that is because this is charged in the first one to V naught, and to this will be added as far as the voltage at this point is concerned. So this plus the voltage across this will be V naught plus V naught sine omega t, and therefore since the voltage across this is V naught plus V naught sine omega t, so this capacitor will be charged to 2 V naught, which is the maximum value of this. Like this you can keep adding units. So this is called one stage. Similarly, next will be this stage, and so on. And each stage will give a voltage of 2 V naught. And suppose you have 10 stages, then you will have 2 into N into V naught. So you can, of course, then the problem of that voltage breakdown will come, and you cannot go infinitely. So now you are connecting this, because ultimate aim, your aim is to accelerate the particles. So you connect an accelerating tube here, for example, with an ion source, and that ion source you enclose in a high voltage terminal, and that is connected to this, and then you have several electrodes, and then you connect these ones here, and the particles will be accelerated and current will flow. When current is flowing, there will be a drain. This will be a drain on the high voltage, and therefore the voltage will slightly come down depending upon how much voltage is dropped across this, because when the current is passing through the accelerating tube, so that is equivalent to a voltage drop, that is shown here as a delta V. So the total V, the voltage will not be 2N V naught, but it will be reduced by a delta V. And of course in this one the entire, because we are using different systems and there is always some variation, and there will be little bit uncertainty in the voltage, and that is called this delta V here. So that actually defines the beam resolution, So, and that is a random, and that is a function of several, for example, breakdown voltages and several factors are taking care of this. Uh, and this V, the delta V, which is a drop, will depend upon how many stages you are using, and this is the empirical relation, and it is 1 by Fc. F is the frequency of the AC voltage, which you are input AC voltage, and C is the capacitance of the entire system. So you can see that if you want to have a very small drop, delta V, then the frequency and the capacitance has to be very large as possible. And of course, you should also have, if number of stages also should be small, then only delta V will be small. Now, all these things are contradictory, because if you have less number of stages, then obviously the total voltage will be less. And if you have high C, then the, as you have seen in the second lecture, that if the capacitance value is large, then the charging of the capacitor takes longer time, and therefore you have to have a smaller C if you want to have very fast. But if you have a smaller C here, then delta V, which is uncertainty in the voltage, will be large, and therefore you have to optimize this equation to in terms of all the three parameters, that is F, frequency, capacitance value C, and the number of stages. And of course you have to also see that voltage drop is also minimized, because as I said in the preamble, you would like to have the voltage as fixed as possible, constantable, and that again is given by this. So that also says, now you see that whatever for delta V, you needed a smaller number of. Here also you should have a small number of stages if you want to have a ripple is as low as possible. And so both of them show that and F and C have to be large, and number of stages have to be small if you want to have both these things as small as possible. And that somehow contradicts the requirements, and therefore you have to find an optimum value of all the three parameters. So while you are designing the Cockcroft-Walton type of accelerator, then you have to keep optimized all these parameters. So in order to keep voltage drop and ripple small, one should choose the frequency F and the capacitance value C as large as possible, and limit the number of stages to number of stages and to as small as possible, and that will not be that is in contradiction with the high voltages you want to have. There is another parameter which you have to be very careful while designing these accelerators, is that electric field at the surface of the electrodes should be kept in such a way that corona discharges are not taking place. Otherwise, not only the voltage will come down, that will be another load, voltage will come down, but also this uncertainty in the voltage and the fluctuation in the voltage, they will also be large. And therefore the sharp edges should be avoided so that corona formation does not take place. The electric field is proportional to 1 by function of R. R is the radius of that sharp surface. So if it is a very sharp surface, the electric field will be very large. As a consequence of high electric field, the voltage breakdown will take place. So you can see here it is mentioned that electric field is equal to V, the voltage, divided by R. but is basically a function of R. So if R is very small, that means if it is a sharp point, then the electric field will be very large and the breakdown will happen and corona formation will be taking place. So all the sharp surfaces should be avoided. For open air accelerators, the electric field should not exceed, empirically it is shown, it is measured that it should not exceed more than 3 million volts per meter. And as a consequence of that, if you want to do all this, then you cannot exceed 1.5 million volts in the case of Cockcroft walton. So that is why, as I mentioned earlier, that the maximum voltage which could be achieved in the case of Cockcroft walton type of accelerator was from 1.25 to 1.5 million volts. Now, when you are using this Cockcroft walton type of accelerators for acceleration of charged particles, then the accelerating tube should have ultra high vacuum, because otherwise when the particles are accelerated and they move inside the accelerating tube and the vacuum is not good, then there will be a lot of collisions and there will be not only there will be loss of energy, but there uncertainty in the energy will also exist. So a high vacuum is needed to minimize the electrons generated from the collisions of ions with the residual gas, because if the vacuum is not good, there will be a lot of residual gas in the accelerating tube. In some accelerators, electron suppressors are used to avoid these things. Permanent magnets are also used in the accelerating tube to deflect those electrons which are generated because of collisions, and therefore they don't get multiplied, and the load is decreased and the breakdown also will be avoided. So these are some of the precautions which we have to take in all the DC accelerators. Now this slide I have shown you earlier, that even the Cockcroft walton type of accelerators were very useful in for many applications, and two applications which were very efficiently done. One was DD reaction and other was DT reaction, and the Q values of these reactions, both of them produce neutrons, and in fact even today the second one is used for generating monoenergetic neutrons of 14 MeV, because the second reaction has a Q value of 17.6 MeV, and depending upon the masses, for example, the kinetic energy will be shared between the products. For example, here, if the D is falling on tritium, is going to helium-4 plus neutron. And the kinetic energy, you can say that from the kinematics, you can say the energy of the neutron will be 4 by 5 times, and that will be about 14. So it is 14 MeV neutrons are produced through this reaction, and from the first one, D plus D, you get 2 MeV neutrons. So these two reactions are very popular, and even the Cockcroft walton type of accelerator was very useful in this. Now these Cockcroft walton accelerators are still used as pre-injector for the large accelerator facilities. In fact, till almost like 80s, they were the only ones which were used as a pre-injector. Of course, in around that time, another accelerator was developed. This is RFQ, radio frequency quarter pole. And now all the Cockcroft walton accelerators have been replaced by that. But till that time, for several decades, it was the unique accelerator which was used as pre-injector even in the hundreds of GeV accelerator facilities, and they were very useful. They are very rugged. They are perfect, and not only in as a pre-injector, but they have also been used for several applications which are listed here, and which you can see that some of them important ones. And since the energies were less than about 1.5 MeV, they could only be used for applications in solid state atomic and solid state physics experiments, ion beam modifications of materials, atomic physics. And now these 14 MeV neutrons have been used for doing demo experiments in accelerator-driven subcritical reactor systems, and they are very useful and they are generating a lot of data. Now the advantages of this Cockcroft-Walton type of accelerator is that, as you have seen, that only capacitors and diodes are used. And using these two simple components, electronics components, you can step up the low voltages to high voltages depending upon how many stages used. So that is one advantage. So you are using only two kind of components, capacitors and diodes. This eliminates the requirement of the heavy core. For example, here you are using a transformer and simple transformer, and bulk of the insulator and potting is required, that you can eliminate. Voltage across each stage of the cascade is equal to twice the peak value of the AC voltage in the half wave rectifier. And advantage of such circuit, this becomes advantage because it is capacitor is charged to the peak voltage. Another advantage is that it needs very cost-effective components, and it is very easy to insulate them. So the whole system is very cheap. One can also tap the output from various stages. Suppose you are having a big Cockcroft-Walton and you don't want to use it, you can tap the voltage from any place and you can use it. One big advantage even today is that high average current, which is a DC voltage multiplier, so high average current can be obtained in this case. So these are some of the advantages. And of course, the disadvantage, as I said, was that the maximum voltage is limited to about 1.5 million volts, and therefore breakdown of the insulations have to be avoided. And if you want to do that, you cannot go to very high voltages. So these are some of the disadvantages. So if you want to go to higher voltages, then you cannot use this. Up to 1 to 1.5, there is no problem. They are one of the very good accelerators, voltage multipliers. And thank you very much.